So in the last class, we have discussed how the osmotic pressure relates to the function that we have discussed earlier, the Helmholtz free energy density. Before that, what we said was that function f of phi characterizes completely the mixing and phase separation behavior. We only have to look at the second derivative of the function. Second derivative is higher than 0 or the function is upper concave, we will have the mixing behavior. If second derivative is less than 0 or the function is convex, we do have a phase separation behavior. So now I will take it further, and then there is one more thing we discuss in thermodynamics very often, that is chemical potential. So today I will discuss how the chemical potential also can be written in terms of the function that we have discussed, the f of phi t, the Helmholtz free energy density. And after that we will talk about what is the thermodynamic origin of mixing. So we have been talking about the fact that the function characterizes the mixing behavior or the phase separation behavior, but then we talk in general about diffusion and try to see like how all these things fall into place, and how does this relate to our ideas of mass transfer that you may have had in the mass transfer course. Okay, so let us talk about chemical potential. So just to recall, chemical potential essentially refer to the change in energy if I add a molecule of an species into the system. That is my chemical potential. We talk in terms of the partial Gibbs energy, that is a derivative of the Gibbs energy with respect to the number of moles. But in more general sense, it is simply the change in energy that we get if I add a molecule to the system. And the chemical potential is very useful if I want to think of the phase equilibrium of two phases when the system has a tendency to phase separate. So the way we define, so again going back to the example we have, where we have a solute plus solvent, that is a binary system. So I can talk about two chemical potentials here, one of solute, that is how much will be the energy change if I add a molecule of solute into the system. So NP characterizes the number of solute molecules, and of course while doing that, the number of solvent, the temperature and the pressure must be held constant. Similarly, I can define the chemical potential of the solvent, which is simply the derivative of Gibbs energy with respect to the number of solvent molecules, that is Ns, while keeping the number of solute molecules fixed and the temperature and pressure fixed. So solute are Np, solvent is Ns, and this is for solute and this is for solvent. Now just to recall, we said that the Gibbs energy G is V multiplied by P plus F of phi t, where this is the function we care the most about, that is the Helmholtz free energy density. And we also said that V is equal to Np Vp plus Ns Vs, and is a constant if the system is incompressible. So if I plug in this value of V in the G, what we get is and again for simplicity I am working with a constant T, but the idea is very general, it will apply to even a variable temperature. Okay. So now if I want to get the mu p, that will be dou g by dou n p. So, using that particular function and using chain rule, what we have is V p multiplied by p plus f of phi plus n p V p plus n s V s, and of course, pressure is not a function of the number for a liquid. So, we have dou f by dou n p, and again since we know that at least for a constant value of V p, we can write n p in terms of phi again. So, using this particular relation, I can write this thing as dou f by dou phi by dou n p. So, we can write dou f by dou n p as dou f by dou phi multiplied by dou phi by dou n p, and now let us see like what the dou phi by dou n p is equal to. So, going back, my phi is equal to n p V p by V, that is n p V p divided by n p V p plus n s V s. So, if I do dou phi by dou n p, that is equal to n p V p plus n s V s multiplied by V p minus n p V p multiplied by V p divided by n p V p plus n s V s whole squared. So, we have a cancellation here. So, this is equal to n s V s V p the following. So, now if I plug in this thing we have derived for dou phi by dou n p in the previous relation that we have written earlier, what we get is mu p is equal to V p multiplied by p plus f of phi t plus n p V p plus n s V s multiplied by dou f by dou n p, which was dou f by dou phi multiplied by dou phi by dou n p. So, the first thing is f of prime phi, and the second thing is what we have just evaluated. So, again we have a cancellation here, and what we get is I am sorry, we have written as f of phi t here, but since we have taken phi to be constant, it is simply f of phi. Again the idea was simply to have a convenient representation, but the equations will hold even at a different temperature. And then we have f of prime phi multiplied by n s V s If I now look at this particular term, it is simply the volume of solvent divided by the total volume. So, it is simply the solvent volume fraction, which is 1 minus of solute volume fraction, and so we can write mu p as Vp multiplied by P plus f of phi plus 1 minus phi f prime of P. So, again just like we did for the case of osmotic pressure, we can also write the chemical potential also in terms of the function f that we have discussed earlier, that is the Helmholtz free energy density. In fact, we can put a temperature back in here because nowhere we have assumed anything to do with constant temperature. The same thing I can do for the chemical potential of solvent, and if I do the derivation, what I will get is mu s is equal to, again it is a function of phi, is equal to V s multiplied by P plus f of phi t minus phi multiplied by f prime phi of t. Okay. Just to recall, I am putting back the temperature here. So, I was just writing f of phi for convenience sake earlier. In fact, I will interchangeably using f of phi t and f of phi, but eventually we will discuss about the temperature effect, and then the temperature part will become useful. But so until so forth, the temperature has not played any role into our mathematical formulation. Okay. All right. So, now if you recall, I will just also write the solute chemical potential term here. So, if you recall from the last class, we have found the expression for the osmotic pressure as, again I can put in the temperature in that relation as well. And now you can see the chemical potential can also be written in terms of osmotic pressure, because you can see this particular term that we see here is common in the previous expressions that we have derived, just a minus of that. So, in fact, we can write the solvent chemical potential as mu s phi is equal to V s multiplied by P minus pi, you can write as a function of phi and t, plus some constant value. So, basically I take up all the values containing f of 0 and all the other constants, which become what I known as the standard chemical potential basically comes from the f of 0 term that we had in the osmotic pressure. That of course does not depend on the volume fraction phi. So, what it gives me is the chemical potential apart from the constant V s can be thought of the difference between the bulk pressure and the osmotic pressure that is present. So, going back to the smoke example, smoke will exert some osmotic pressure, but ultimately it depends on the existing pressure in the room. So, let us say if the room is at a very low pressure, then in that case the osmotic pressure will of course win and we will have a high mixing. On the other hand, if room pressure is also high, then in that case the pushing in will have little effect. So, ultimately we can think of the mixing behavior in terms of not really the osmotic pressure, but the difference between the bulk pressure and the osmotic pressure. But nonetheless, the key idea that a single function f describes all that we care about thermodynamically speaking is really true, because we can write the Gibbs energy in terms of f of phi, we can write the chemical potential in terms of this, we can write osmotic pressure in terms of this, and now as I will demonstrate, we can also talk about phase equilibrium in terms of the function f of phi, and that way, without knowing the function even, without even talking about what the function is, we can already talk about that what forms of functions will give what kinds of behavior. So, now I want to take up these ideas that we have discussed and go back to something that you may have learnt in the mass transfer or in treatments of diffusion. Okay. So, you may have learned that things go from a higher concentration to a lower concentration, that is how we characterize mass transfer. To be more accurate, things go from a higher chemical potential to a lower chemical potential, that in turn depends on the concentration gradient. So, how does that idea of diffusion relates to the this function f that we have discussed, and how does it fit into the scheme that we have been developing in solution thermodynamics? So, let us think of the thermodynamic origin of diffusion So, what do we care about? We care about a gradient in the chemical potential. Things move from a high chemical potential to a low chemical potential. So, we are interested in terms like dou mu p by dou phi and dou mu s by dou phi. How does the chemical potential changes with the change in phi? So, we already have obtained the expression for mu p right here. So, I want to take a derivative of that with respect to phi. So, let me first reproduce here. So, mu p is equal to V p multiplied by p plus f of phi t plus 1 minus phi f prime of f of phi t. So, if I take a derivative, that is equal to V p. So, p of course does not depend on composition. So, we have f prime of f of phi t plus 1 minus phi f double prime f of phi t minus the derivative of 1 minus phi is minus 1 f prime f of phi t. So, again we have certain cancellations, and what do we get is V p multiplied by 1 minus phi f double prime of f of phi t. Okay. So, if I do the same thing for the chemical potential of the solute, then the mu s was equal to V s multiplied by p plus f of phi t minus phi multiplied by f prime of phi t, and if I take a derivative with respect to the volume fraction, I will get V s multiplied by f prime phi t minus phi f double prime phi t minus f prime of phi t, and we have cancellations, and what we get is V s minus Vs phi multiplied by F double prime phi t. Okay. So, now let us go back to the original idea that for mixing F double prime is higher than 0, that came from the concave nature of that. So, if F double prime is higher than 0, we can see from here that dou mu p by dou phi is higher than 0 and dou mu s by dou phi from the expression here must be less than 0. Now, since things go from a higher chemical potential to a lower chemical potential, and what we see here is mu p is increasing with increasing phi and mu s is decreasing with increasing phi, the chemical potential will decrease when the phi decreases. That means, going back to the chamber analogy, so if you think of a membrane again, for the solute particles, if they move to the right, that results in a decrease in the volume fraction of solute. This must be favored because this is a process going from a high chemical potential to a lower chemical potential. On the other hand, for the solvent particles, as the volume fraction increases, you will have a lowering of the solvent chemical potential. So, solvent will try to mix with solute, because when it mixes with the solute, the volume fraction increases and that results in a lowering of the chemical potential. On the other hand, when we have mixing of solute with solvent, the solute chemical potential decreases because it starts with a higher phi. Due to mixing, it results in a lowering of phi. So, in both ways, this is actually characterizing a mixing behavior. Okay. So, if the analogy is somewhat confusing to you, let us start with say a concentrated solute solution that has a very high value of volume fraction phi, and let us say I mix into a pure solvent. So, when I mix in, then the volume fraction of the solute decreases when compared to the initial concentrated solution of solute, and this is a favored process because the chemical potential of solute is decreasing. It is going from a high to a low chemical potential. In the same problem, if I now look at the solvent phase also goes to a lower chemical potential when the solute is added into it. Okay. So, the motion of the solvent and solute are actually opposite of each other. That is what results in the mixing behavior. Okay. If on the other hand, if we have a phase separation, then F double prime is less than 0, that is when dou mu p by dou phi is less than 0 and dou mu s by dou phi is higher than 0. Now, it means that mu p decreases with increasing phi. So, if mu p is decreasing with increasing phi, then the concentrated solution will prefer remaining concentrated, it will not like to be dilute. On the other hand, the mu s is actually increasing with increasing phi. So, the pure solvent will prefer remaining pure solvent because when it mixes with the solute, the volume fraction increases and the chemical potential also increases. Okay. So, the model here that I will draw is, let us say this is my concentrated solution, and if I mix with a dilute solution. So, this is concentrated and this is dilute. So, ultimately for them to mix together, solute molecules should be going that way and solvent molecules must be coming this way. Solute molecules will go in the dilute phase if the chemical potential is decreasing in that direction, and that will only happen when F double prime is higher than 0. Similarly, solvent molecule will go in the bottom phase only when then F double prime is higher than 0, because that then results in the lowering of chemical potential of solute. So, the mixing only happens when we have a positive value of the second derivative of F. Okay. So, now we can see that this whole idea of the mixing and phase separation that we started with basically explains or relates the concepts of osmotic pressure, chemical potential that we have discussed in thermodynamics classes. And now I want to take it further and talk about the phase equilibrium, that is when the things phase separate, and let us say the system prefers to remain phase separated as opposed to mix. That will be the case when F double prime is less than 0. But when it is phase separated, then we can talk about a phase equilibrium that is given by the equality of chemical potential. So, how can we use the idea of F of phi t, that is the Helmholtz free energy density, to characterize the phase equilibrium? So, again the whole motivation of the exercise is to simplify our analysis of thermodynamics to a single function in the case of a liquid solution, and then we will go on talk about polymers, and we try to argue what that function should be based on some simplistic models that we will discuss. Okay, so with this I conclude this lecture. Thank you.